So we're going to go ahead and work some additional practice problems for Chapter 8. Again, if you're watching this video, you are clearly on YouTube or linked through D2L to watch these. I recommend working these problems on your own first to make sure you're comfortable. Once you know you're comfortable with them, then go ahead and you can start working them, looking at the key, looking at this video. This key is only written out in this video, so you must watch this to get the actual key. But let's go ahead and work through a series of problems for the content from Chapter 8. So number 1, calculate the wavelength of an electron that's traveling at 2.65 times 10 to the 6 meters per second. Here we've got your velocity and we've got wavelength. We can use our de Broglie equation to solve this question. The de Broglie equation is relating that wavelength of a particle to its velocity. So now we know wavelength equals Planck's constant divided by the mass times velocity. So h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. M is your mass. This is in your SI-based units. SI units for mass is actually kilogram. We use gram all the time, but it is kilogram. An electron weighs 9.11 times 10 to the minus 34, or 31, I apologize, 31 kilograms. The only reason I remember this is that for some reason I just think of 911 and then I think of Halloween and it clicks for me. I'm trying to make this a lowercase k. I'm not doing a very good job. You don't have to know the mass of the electron. On an exam or quiz, I would give it to you. Since this is additional work outside of class, you guys can look that up. And your velocity, remember v is velocity, nu is frequency. They look very similar in font. 2.65 times 10 to the 6th meters per second. So now it's just a plug and chug type thing. 6.626 times 10 to the minus 34 joule seconds divided by 9.11 times 10 to the minus 31st kilogram times 2.65 times 10 to the 6th meters per second. If I plug this in my calculator, I'm going to get an answer of 2.74 times 10 to the minus 10th meters, which I can also rewrite as 2.74 angstroms. You guys haven't learned angstroms explicitly, at least not in my class, but angstrom is 10 to the minus 10th, and it's often how bond lengths are measured. But the bigger question is, how the heck did I get to meters from the units I had above? This is where we need to remember that joules is what we call a calculated unit. A joule is a kilogram meter squared per second squared. So I've got that times a second divided by kilogram times meters per second. My kilograms are going to cancel. This second cancels with one of my seconds here. One of my meters here cancels with meters here, and my last second here cancels with seconds here, leaving me meters for my final answer. Joules will throw students off, so you need to be comfortable with that and understand that joules are, in fact, kilogram meter squared second squared, or per second squared. You can also write that as kilogram meters squared second to the minus 2. That the minus sign shows you it's the denominator, but you need to remember that so you can get to the correct units here. What is an emission spectrum, and how does an emission spectrum of a gas in a discharge tube, think of lab, I know you guys haven't done this in lab, so that comment's probably not as helpful to you, differ from a white line spectrum? Some people, most schools do this do a lab like this in lab, and unfortunately you guys don't have a first semester lab here, so you guys didn't get to do it, but a lot of students do this in lab. Anyway, let's go ahead and look at it. What do I mean by this? What's an emission spectrum? Emission spectrum, first of all, emission spectrum is when the electrons are going back down to their ground state. So the energy is being emitted in the form of light. So the light's released, the electron when that light releases or allows the electron to travel back down to its ground state, it releases that energy in the form of a photon, h nu. So the electron travels from the excited state back down to the ground state, and when it does that, it releases a photon. Again, we use h nu to represent a photon because that's going to represent the energy of the specific photon being released. So line spectrum is what we see from a gas discharge tube. When we see this, what we're going to have here is you're going to have some kind of spectrum, and it will all be black in here. But you're going to have very specific lines. So you'll have a purple line, maybe a blue line, maybe a red line. It's very discrete lines. A white light spectrum, on the other hand, is just that. It's the entire rainbow. So you'll have your red into your orange, to your yellows, to your greens, blues, indigo, which I never remember what indigo actually looks like, and purple. So white light spectrum is continuous lines. Again, this is why if you actually see somebody wearing a white shirt, they're actually reflecting every color in the rainbow back at you at one moment in time. It's taking the light from the sun or whatever light source it has, and it's reflecting all colors back at you at the exact same moment in time, and your brain is processing that as white. If you see black, it's because it's absorbing all color and all you see is nothing. So, what is the characteristic wavelength associated with a baseball thrown at 95 miles per hour? We're given that the mass of a baseball is 5 ounces, 16 ounces is 0.4536 kilograms, and 1 mile is 1.609 kilometers. Well, to do this, I need the de Broglie equation. So lambda is going to equal h over mv. Because I want wavelength. I need to know that. I've got velocity here. So I know that I'm going to be dealing with the de Broglie equation. H is Planck's constant, 6.626 times 10 to the minus 34 jouleseconds. M is mass, but I need this in kilograms. I currently have this in ounces. And V is velocity, which I need in meters per second to cancel out my joules. And I currently have it in miles per hour. So I will have to do a series of conversions before I can actually use my equation. Let's go ahead and convert our mass first. The mass of the baseball is 5 ounces. 5.0, don't forget that 0.0 is your sig figs. I've got 0.4536 kilograms for every 16 ounces. I've been asked a couple times now by students if I need to keep the 0 here. The answer is yes. One, sometimes students will write such a little point and then they'll write 4536 and they forget that decimal point. They don't see it and it messes up their calculations. Two, it's just proper. So yes, please include that. This equals 0.14 kilogram. 2 sig figs, 2 sig figs. I also need my velocity in meters per second. I've got 95 miles per hour. Now again, you can convert the distance first or the hours first. I'm going to convert the distance first just because it's the numerator. Times 1.609 kilometers per 1 mile times 1,000 meters per 1 kilometer. If I stopped right here, this cancels my miles and my kilometers, and I've got meters, so I'm halfway there. Now I just need to convert my time. I know that there is 1 hour for every 60 minutes and 1 minute for every 60 seconds. Cancels my hours, canceling my minutes. I've now got the units I want. Calculate this out, and I get 42 meters per second. 2 sig figs, 2 sig figs. Now let's go ahead and make some room on the slide. So now we're ready to go ahead and use the de Broglie equation. Lambda equals 6.626 times 10 to the minus 34 joule seconds divided by the mass, 0.14 kilograms. Don't forget that zero, that leading zero. It's just a placeholder. Times 42 meters per second. Calculate this out, and we get 1.1 times 10 to the minus 34 meters. And we just learned 2 examples ago how we can get all these units down to just meters. So if you're unsure of how we got to meters there, please look at example 1, and you'll see how that does in fact give us meters. And see, that is a perfect example of drawing the decimal place and it not really showing up. 1.1 times 10 to the minus 34 meters is the wavelength of the baseball thrown at 95 miles per hour. It's a pretty long wavelength. 95 miles per hour seems fast to us, but in the terms of wavelength and correlated back to energy, it's really not that fast. Calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. So, wavelength, we're looking for wavelength here, and we're given frequency. We know lambda is equal to c over nu. C is our speed of light. 2.998 times 10 to the 8th meters per second. 100.7 megahertz. Megahertz is 10 to the 6th hertz, so I need to convert that. You can do this in a separate equation or in this equation together. I'm going to do it in the same equation. 10 to the 6th hertz for every 1 megahertz. I get out 2.98 meters. Radio signals are pretty long, relatively speaking. You should remember the electromagnetic spectrum, and they're on the long, low energy side, so it makes sense that it's a longer wavelength. Which of the visible colors of light has the highest frequency? And what does this mean about its wavelength? Well, this is where, remember, I want you to be careful with this. What do we mean by energy, frequency, and wavelength? So the electromagnetic spectrum, we usually write it with our radio waves all the way to our gamma rays. Increasing this way is our wavelength, but increasing this way is our energy and our frequency. So, visible colors of light is our Roy G. Biv. Visible colors meaning what colors do we see. But I warned you guys that the way we memorize this is actually backwards to the electromagnetic spectrum. So this actually goes V, I, B, G, Y, O, R. If we want to correlate it on the wavelength or on the electromagnetic spectrum itself. So which one has the highest frequency? Violet, which we often call purple. What does this mean about its wavelength though? Well, we know that the higher the frequency, Because remember, frequency is cycles per second. Means higher energy, but shorter wavelength. This compared to this. If this is 1 second, if this distance here is 1 second, we're getting more of a wave in here, more of a complete cycle than we are over here, partial cycle. So higher frequency, higher energy. So let's go ahead and look at a couple more examples like we just did in number 4. Calculate the wavelength of each frequency of electromagnetic radiation. I know this may seem repetitive, but these equations, those should be like muscle memory for your brain. You need to be able to quickly see them and be able to calculate it quickly. So if we see calculate wavelength for each frequency, we know we can use the relationship lambda equals c over nu. C being your speed of light. Now, I memorize this as 2.998 times 10 to the 8th meters per second. You are fine memorizing this as 3.00 times 10 to the 8th meters per second. They have different number of sig figs though. So depending on what other values you're given, you need to pay attention to your sig figs here if this limits it. If it does, that's fine. I don't care. This has 3 sig figs, this has 4, but make sure you're using the right number of sig figs in your final answer. So 2.998 times 10 to the 8th meters per second divided by 100.2 hertz. A hertz, 1 hertz, equals 1 second to the minus 1. It's 1 cycle per second. So I'm going to replace this with seconds to the minus 1 just so it's very clear on my units here. When I calculate this out, I get 2.992 times 10 to the 6th meters. 4 sig figs, 4 sig figs, 4 sig figs. Again, if you'd use 3.0 there, you would have 3 sig figs here. And 1070 kilohertz. Lambda is equal to c over nu, 2.998 times 10 to the 8th meters per second. 1070 kilohertz. A kilohertz is 1,000 times greater than a hertz. Takes 1,000 hertz to reach 1 kilohertz. And when you make sure you're calculating that out correctly, when I calculate this out, I'm going to get 280, but I need to put a decimal place here, meters. So I have 3 sig figs here. This 0 is not significant on the end, but my final answer was 280. If I write it like that, that's only 2 sig figs. I must include that decimal place to specify that that 0 is in fact significant. Calculate the wavelength in nanometers of light emitted when an electron and a hydrogen atom makes each transition. Remember, you can do this either separately or together. I do the equation together. You can calculate each one by itself, meaning that you can calculate negative 2.18 times 10 to the 18, negative 18 joules times 1 over n squared, and then subtract the second one from that and do those in pieces. I do this all in one piece though. I'm going to do this as this equation, n squared final minus 1 over n initial squared. I want wavelength in nanometers of light. If I'm transitioning between two things, I'm only calculating energy. So I'm also going to have to use E equals hc over lambda, rearranged, to calculate my wavelength. So for the first example, n equals 2 going to n equals 1. This is n initial, this is n final. Negative 2.18 times 10 to the negative 18th joules times 1 over 1 squared minus 1 over 2 squared. Be careful plugging this into your calculator. Use parentheses when appropriate. And you should find the answer to be negative 1.64 times 10 to the negative 18th joules. Why is the answer negative there? Well, I'm going from an n equals 2 to an n equals 1 level. I'm emitting light, so I'm losing energy. So therefore, it's negative sign, and the negative is just representing that the energy is being given lost from the electron, not from it being gained. That's the only reason it's negative. I'm going to take the absolute value of that and make it positive when I do the calculation for wavelength, because wavelength is a distance. It's not going to be a positive or a minus sign on the wavelength. Lambda equals 6.626 times 10 to the minus 34 joule seconds. C is your speed of light, 2.998 times 10 to the 8th meters per second. And the energy we just calculated, 1.64 times 10 to the minus 18 joules. Again, I'm keeping this as a positive here because the negative or positive is just telling me the sign on the energy is it being gained or absorbed or emitted. I'm emitting that energy, and that's why it's negative. I don't want to actually give myself a negative distance, though. So I find here the wavelength to be 1.21 times 10 to the minus 7 meters. And n equals 2 going to n equals 4. This means n equals 2 is n initial, n equals 4 is n final. That, in this case, the energy is actually the photon is being absorbed, exciting that electron to a higher energy level. Negative 2.18 times 10 to the negative 18 joules. 1 over 4 squared minus 1 over 2 squared gives me 4.09 times 10 to the negative 19th joules. Again, positive in this case because the electron gained that energy to emit up to a more excited energy state. Plug all of this in. Lambda 6.626 times 10 to the minus 34 joule seconds. Speed of light 2.998 times 10 to the 8th meters per second. And the energy we just calculated, 4.09 times 10 to the negative 19th joules. And I get 4.86 times 10 to the negative 7 meters. Make sure you're comfortable doing these calculations for the transitions of the electrons between the different energy levels. Which electron is, on average, closer to the nucleus? An electron in a 2s orbital or electron in a 3s orbital? Well, remember, what do these 2s and 3s mean? The 2 and the 3 tells you your energy shell. So you've got your nucleus with your protons and your neutrons hanging out. And then you've got your shells. N equals 1, N equals 2, N equals 3, and so forth. In the N equals 1 level, we have 1s orbitals. In the N equals 2 orbital, we have 2s and 2p orbitals. In the N equals 3, we have 3s and 3p and 3d orbitals. N equals 4, 4s, 4p, 4d, and 4f. And then from then on, we've got 5s, 5p, 5d, 5f, etc. of each type of orbital. But that means that the nucleus is here. So closest to the nucleus is our 1s. But if I'm comparing 2s and 3s, I see 2s is in fact closer to our nucleus than a 3s orbital would be. So you need to think about what those orbitals mean in relation to the structure of the atom itself and where they reside. What are possible values of L for each value of N? What is L? L tells me the type of orbital I have. meaning is it S, P, D, or F? L equals 0 gives me an s orbital. L equals 1 is P. L equals 2 is D. And L equals 3 is F. L is equal to n minus 1 and anything below that. So if what I mean by that is n equals 4, I can have L equals 3, L equals 2, L equals 1, down to L equals 0. It's always L equals 0 up to the value of n minus 1. So if n equals 1, that means L can only equal 0. If n equals 2, L can equal 0 or L can equal 1. If L equals 3, if n equals 3, should be an n there, L could be equal to 2, L could be equal to 1, or L could be equal to 0. And if n equals 4, L could be equal to 3, to 2, to 1, or to 0. This would be an s orbital. These are p orbitals, d orbitals, and f orbitals. Again, quantum numbers are just the address of the electron. They're just a mathematical way for us to describe where these things reside. What are the possible values of m sub L for each value of L? What is m sub L? M sub L is equal to negative L through 0 through positive L. So if L equals 0, m sub L has to equal 0. M sub L also describes the orientation of the orbital. Because remember, s orbitals, we only have a sphere. That should be a sphere. P orbitals, we have px, py, and pz. So we've got dumbbells. D, we have 5 options, and F, we have 7 options. M sub L is telling me which of those options I have. So if L equals 0, we can only have m sub L equal to 0. This is going to represent an s orbital. If L equals 1, m sub L can equal negative 1, 0, or positive 1. These are the 3 p orbitals. If L equals 2, m sub L will equal negative 2, negative 1, 0, plus 1, and plus 2. Your 5 d orbitals. And if L equals 3, m sub L is equal to negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3, which is your 7 f orbitals. Sketch the 1s and 2p orbitals. How do they differ and how many electrons does each orbital hold? 1s is a sphere. 2p is your dumbbells. So this is your 1s. This is 2p, 2p, and 2p. Each shape holds 2 electrons. So this holds 2 electrons. This in total holds 2 electrons. this holds 2 electrons, and this holds 2 electrons. So the s orbital holds 2 electrons total, while your 3p orbitals hold 6 electrons total. S is a sphere. Oops. P is, I call them your dumbbells. Other people call them bow ties. Whatever you want to call them. But that's the difference in shape. And then these will actually have opposite, talk about this in another class, but one side will be shaded in, one side will not. So they're slightly opposite of each other, but this makes up your 2p, 2px, 2py, 2pz. Okay, number 12. The emission spectrum of sodium consists of 2 closely packed yellow lines around 589 nanometers. What is the frequency of 589 nanometers of light? Well, I know that lambda equals c over nu. So I'm going to rearrange that to solve for frequency, or nu, which is equal to c over lambda, your speed of light over your wavelength. Okay, the Passion series. This series, basically, there's a number of men that figured out certain electronic transitions for hydrogen specifically, where they all had emissions where electrons fell from higher energy levels to a specific energy level. So this series is specifically when things fall to the n=3 state. There's the Balmer series, Passion series. There's a few others too. I don't remember all their names, but I recognize them when I see them. But this series of atomic emission spectrum occurs in the infrared portion specifically, because it's a specific wavelength. And the lines in this series result when an electron makes a transition from a higher energy state to the n=3 energy state. One of the lines in this series has a wavelength of 1093.8 nanometers. I want to know what energy state was the electron originally in, which means I'm falling to the n=3 state, and I'm at some other level up here, and I've got an electron that's going to emit a photon at 1093.8 nanometers and fall to this level. And I want to know what is this original level. So a few things I need to do this. Well, first, I know that I can calculate the energy of that transition. Energy equals hc over lambda. I'm going to solve this and find this energy. I also need to use my Rydberg constant equation, negative RH times 1 over n final squared minus 1 over n initial squared to find what I had as my n initial. So let's go ahead and solve the energy first. E equals hc over lambda. This is equal to 6.626 times 10 to the minus 34 joule seconds times speed of light, 2.998 times 10 to the 8th meters per second, divided by our wavelength, 1093.8 nanometers, but I do need this in meters to cancel things out, so times 1 meter divided by 10 to the 9th nanometers. Nanometers cancel, meters cancel, seconds cancel, and I'm left with joules, which is a unit of energy. This gives me 1.82 times 10 to the negative 19th joules. Now, the trick here is that this just cares about the energy of this transition. It doesn't care if it's positive, negative, whatever. Because remember, we're looking at wavelength there, and wavelength is a distance. But because I'm falling from a higher energy level down to n=3, when I use this in the next part, I need to make this a negative 1.82 times 10 to the negative 19th joules to represent that a photon of energy was lost. So, go ahead and use our next equation. I'm going to put negative 1.82 times 10 to the negative 19th joules equals negative 2.18 times 10 to the negative 18th joules times 1 over 3 squared minus 1 over n initial squared. When you solve through for this, first you can take the negative 1.82 times 10 to the negative 19th joules, divide that by negative 2.18 times 10 to the negative 18th joules, and I'm going to say 1 over n initial squared is equal to 1/9 minus 0.083486 I'm going to clean this up a little bit more. 1 divided by 1/9 minus 0.083486. This is going to be equal to n initial squared. I'm going to take the square root of both sides of these, though, to get rid of that square. And what I'm going to find is that n equals 6. So for wavelength of 1093.8 nanometers, in the Paschen series specifically, this means that my initial energy state, the electron was originally in the n equals 6 energy level. It dropped from n equals 6 to n equals 3, and it released a photon of light with a wavelength of 1093.8 nanometers. And our last example in this chapter, a microwave oven heats by radiating food with microwave radiation, which is absorbed by the food and converted to heat. Suppose an oven's radiation wavelength is 12.5 centimeters. Okay, I'm going to highlight that because that's important to me. 12.5 centimeters for a wavelength. A container with 0.25 liters of water, that's also important, was placed in the oven, and the temperature of the water rose from 20 degrees to 100 degrees C. Also important. I want to know how many photons of this microwave radiation were required. Assume all of the energy from radiation was used to raise the temperature of the water. Why does it say that last sentence? That last sentence is just to basically reiterate to us that no energy was lost elsewhere. We can assume that all of the energy went straight to raising the temperature. So, what do I know here? Well, I know I've got a wavelength equal to 12.5 centimeters. I'm going to convert that to meters because I'm going to need it in meters to be able to do the calculations for energy. 12.5 centimeters is the same as 0.125 meters. If you're unsure, write out the conversion, but 1,000 centimeters equal 1 meter. I know E equals hc over lambda, and I'm going to need to know that amount of energy soon. So let's go ahead and calculate that. E equals hc over lambda. H, Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Speed of light, 2.998 times 10 to the 8th meters per second. And lambda, 0.125 meters. We see our seconds cancel, our meters cancel, and we are in fact left with joules as expected. And this gives us 1.58. I'm going to carry an extra number right now, 589. I do need 3 sig figs, but I'm going to carry that extra 9. I'm not going to round quite yet. Times 10 to the minus 24th joules. This is the energy, though, for one photon. Now, I need to know how much energy do I need overall, how many photons do I need to raise this temperature for 0.25 liters of water up from 20 degrees C to 100 degrees C. How the heck am I going to do that? Well, I need to figure out how much energy do I need in total. Then I can figure out how many photons I need. Q equals MC delta T. You guys thought you were done with that equation? No, not even close. That equation haunts us for the rest of time. Not haunts us. It's a great equation. It really is. But I want to use this equation to figure out how much heat do I need to actually heat up 0.25 liters of water. My mass of my water, well, I've got 0.250 liters of water. But the density of water is approximately 1. So I'm going to say this is approximately 0. So 0.250 liters of water. I'm going to use the density approximately 1 gram per mil. This is liters, though. So I've got 1,000 milliliters per 1 liter. That cancels liters out. That cancels out milliliters. So 0.250 times 1,000. Making sure, yes, okay. Sometimes I get tired and I don't convert well, so I like to check it to make sure that I am correct. It is 250, if I could write it correctly. 250 decimal grams of water. So 0.250 liters is about 250 grams of water. Specific heat of water. You guys should have this memorized from first semester, 4.184 joules per gram degree C. That means it takes 4.184 joules to raise 1 gram of water by 1 degree Celsius. And change in T is always T final minus T initial. Whenever you see that little delta, little change in it, always means final minus initial. And I'm going to need space, so I'm going to move this up here. Move this here. And I'm going to shrink this guy down a little bit. Okay, so let's go ahead and plug it into our equation. Q equal to 250 grams of water, specific heat of water. T final, I'm going to 100 degrees C. I'm starting at 20 degrees C. So 100 minus 20 is 80.0 times 4.184 times 250. Q is equal to 83680. Look at units quick, grams canceled, degrees C canceled. This is joules. We do need, this is 80.0, so 3 sig figs for 3, our sig figs are here, but I'm just going to hold on to that for a sec. I want to know how many photons for this whole thing, though. I know that 1 photon is going to release 1.589 times 10 negative 24 joules, a total of almost 84,000 joules. So, number of photons.